So let's take a look at boundary conditions. Boundary conditions are a set of equations which are necessary and useful that apply to boundaries such as charge layers, a metal surface, with and without charge. Potentials can also be described at boundaries. So let's look at the components of E at a thin charge sheet with a charge density sigma. So that's an interface we can explore in terms of the E field. Well, we'll take a surface that looks like this. It doesn't have to be flat. Has a charge density sigma, which does not have to be constant. We build a pillbox around a region on that surface. Now the deal is that we want to use Gauss's law in a simple way, and so we're going to do a couple things. One is that the box penetrates the surface, so there's an area down below and an area above. The thickness or height of this box is epsilon. The ends of the pillbox have area A. They're parallel to the surface, which means that these are small enough features here that we don't have to worry about this curvature. So it's in this region it's flat just on the scale of capital A. The differential of area, so suppose you had a little area here, is normal. The vector that represents that is normal to the surface, and that's true everywhere. So remember that there's a ds for above and there's also a ds below, and I'll just schematically draw it here. There's a directionality to the surface up and down. So A is small enough that the surface appears flat, as I've said. A is small enough so that we can consider the E field that is penetrating that area is constant over that area. This is going to be small. We don't have to worry about the E field penetrating this side here because we make this small enough that compared to this surface, that contribution can be ignored. So let's apply Gauss's law to the system that we've described, and we're only going to consider the normal component if ds is normal to the surface, and we're only worrying about the normal component. Then the left-hand side is very easy because we'll have on the top, we'll have this term here, so that's the E perpendicular above times A, and then the other one, because the normal vector points in the opposite direction, will be E perpendicular. This should be below, so below times A. We can then look at the right-hand side, which is the enclosed charge, which would be sigma times the area, which would give us a Q, divided by epsilon naught. So here's the condition for sigma A equals Q enclosed. Rewriting Gauss's law then in terms of the equality of these two sides, we would have then this quantity here for the two components of the E field, and then here's the right hand side. So you'll notice that A is in all of the factors. We can divide by that, so we end up with this condition right here, that the change in the E field when we have above and below these two quantities is equal to the charge density divided by epsilon naught. What this says is there always is a discontinuity of the normal component of E across the charge layer, assuming that it's not zero. This is a necessary consequence of Gauss's law. Now let's look at the parallel component. We're going to be looking at the components that are along the direction of the surface. So we're going to do the same thing. We're going to make these elements here small enough that we don't have to worry about, for example, E changing here. We don't have to worry about the sides of this loop. Obviously we're going to be using a loop. So half of this loop is above, half of the loop is below, and these are the directions of integration around the loop. So this is the curve C, and it has a length little l and a height epsilon, and the longer parts of the loop are above and below the charge layer. So we make L small enough such that the sigma along that line and the E field are constant along these regions right here. So this is not too long to have changes in E or sigma. And we've already mentioned that if we make this small enough, we don't have to worry about the integration along this part of the loop. So we can ignore any contributions on these portions of the curve. We use the fact that if we take the E field and integrate on any path that closes, so that's what this circle means, we'll end up with zero. And if you remember that that's consistent, actually we can say it comes from the conservation of energy. So if this is zero, if you take a look at the line integral, the first thing you have here is the component that's in this direction here, and that will be E above parallel, because we're only considering the parallel component, which then survives this dot product, and we get an L for the L component of the path. And then we'll have the opposite sign because we're going in the opposite direction, and so we have E below parallel times L. And because the integral of this is equal to 0, these two components with the minus sign in fact is the integral, and that's equal to 0. Well, you can see that because this is 0, you can throw away the L's, and so you end up then with the E above parallel equals E below parallel. So the parallel components of E, those are continuous across the charge layer. So this is restating it. The parallel or tangential components of E being continuous is a consequence of the fact that the line integral of E over a closed loop is 0. So all of this boundary condition results depends on fairly fundamental laws that we've already discussed. So now let's combine these two boundary conditions. When we combine them, we can state the boundary condition for the total E vector. So we're looking at the boundary condition for this E total. If we look at E total, then it's interesting to look at the difference between the E above and the E below, the total values of these quantities. So these are vectors. Well, we can break those down in terms of the perpendicular component and the parallel component. And so this is the unit vector normal to the surface, and this is the tangential vector. If we take this quantity here, then that's going to be the normal vector of this difference here. And likewise, this is the tangential component of this difference, which is of course a vector. And I've already stated what these vectors are. Well, we've already shown that the tangential term is equal to 0 because the E parallel above is equal to E parallel below. So that only leaves the normal component, and here's the condition we've derived. That difference in the E perpendicular is equal to sigma over epsilon naught. So we can combine all this by just basically throwing this part away. The total E vector above minus the total E vector below will be equal to this vector right here. So it's the sigma over epsilon naught times n hat. So this is the discontinuity of the E total vector. Yeah, I just want to point out that n is in one particular direction. We take it below to above. You say, well, how do you know what's below and what's above? You don't. You just take one and stick with it. Doesn't matter. If we look at this E behavior with an external field or a charge layer, let's take this to be the charge layer here. When we're finished with the two vectors that are above and below, so there could be an external field, and I'll show you what I mean by that. So this is the vector of the E field below the surface, and this is the E vector above. Now let me just show you what we have here. So here's the E vector perpendicular below, and here's the E vector perpendicular above. These are just perpendicular components of these two vectors. Well, notice that this one is smaller than this one, and the reason is because the normal component has increased. And the reason for that is because of this quantity right here. So the normal component change is equal to sigma over epsilon naught. So if you look at this component below, this component here, it's bigger because we're assuming this to be a positive number. So that change is what we have here. Okay, now let's look at the tangential components. Those don't change. Remember, we had this condition right here. So these stay the same. Okay, so if you look at what happens then, right in the region of the surface, it basically looks like refraction. Turns out it's kind of backwards, but nevertheless, it changes direction and changes magnitude when you go from here to here. And the beauty of the boundary conditions is it tells you exactly what that change is. So let me just redraw that. The first thing is to realize if you look at this picture here, it's deceiving because what we're really talking about are points very close to the surface on both sides. So really we should draw it like this. So in other words, here's the E vector below, evaluated right here. We put the tail right where it belongs. And here is the E vector position at the point where we're looking at the E vector, which is just above. If it makes any sense to put the tails at the points, this is what it would really look like. Let's look at another uniform E field before the charge. We're looking at this whole thing as if we had this condition here. This is where we're going to put the charge layer. But this is the E field before we insert this. Now, to be very fussy, this vector here should originate from a point right here, and this one originates here. Just don't forget, this vector here represents the vector at a position just below the surface. So what we're going to do is throw in the charge layer. So we're going to slip that in, nobody's looking, and so here's the charge layer. Now remember that the E field above is in the normal direction. If this is positive, it's going up, and so our unit vector is the one that points up, unit vector here, and the vector itself at any point is sigma over 2 epsilon naught times that unit vector. Well, remember there's E field on the other side, and that's just minus this. So we keep the same unit vector n, as I've mentioned before. So let's add those two together, and this is what we get. Now look carefully. You have this vector here, and you're adding this vector. So let me just show it here. So we're adding this vector down here. So what's it do? Well, it tips the vector and reduces, in a sense, the perpendicular component here, because this is normal to the surface. On the other hand, up here it adds it. So this is the vector above, so we have a plus sign here. This is the vector below, here it is, minus. And so E above minus this quantity is this vector, plus this quantity is this vector here. So we end up with a picture that looks what I drew here. It's just schematic. See what happens then when we add these two figures. Okay, now I've shown you here a very particular case, but I wanted you to realize what's causing these changes in the E field. It's really the presence of this charge layer that causes the whole thing to change. To repeat then, this expression here is general. This one's a particular example to show you how that happens, how the change in this actually happens because of the presence of that charge. Okay, well, what about the potential? So we've got these two sides of the surface. Let's take these 2 points on each side of the surface, A and B, and we're going to consider a path that we might be integrating over to go from A to B. And so let's examine that. Well, we've derived an equation before that says that the change in potential between 2 points, and I've chosen those points, this could be B and this A, so the potential above and the potential below is given by this integral here, which is the integral of E dot dl minus sign from A to B. So let's let these 2 points get closer and closer. So we're going to keep them on 2 sides of the charge sheet, but we're just going to get them very, very close. So if we do that, then this quantity here will go to 0 because we're making the length of that line go to 0. So that means then that the change of potential is equal to 0, or potential above is equal to the potential below in spite of the presence of this charge layer. So we conclude then that the potential is continuous across this charge sheet. What about the gradient? Well, it's pretty simple because we know that the E field is minus the gradient of the potential. Remember that this right-hand side is a vector. If we look at the change, this is the equation we had for the change in the E vector related to the surface charge density. This is a vector, this is a vector, and that of course is a vector. We put the minus sign in for the potential above, and we put a minus sign in here for the potential below, but the change in the E field, remember, was minus here, so this becomes a plus. So this is E above, this is E below. If we change the signs and take the dot product with the n hat vector and we use the quantity partial of v with respect to the n variable, which is the variable that's normal to the surface, then this would be equal to del v dot n hat. Okay, so what we mean then is if we have a surface here and we have an n vector like this, n hat, then when we dot this vector with n hat, we get the component along the n direction. And so that's equal to this quantity here. So what we call that, by the way, is the normal derivative of the function, and that happens to be v. And what that means is it's the rate of change of v in the direction normal to the surface. So putting that all together then, because we changed the sign, we have a minus sign here, and this is the boundary condition for the gradient of the potential, and it's given by the normal derivative of v above and below, and we get minus sigma over epsilon naught. Well, let's check boundary conditions for a charge sheet without any external field, which is what we showed you before. And so we have the vector with magnitude here, sigma 2 epsilon naught, same magnitude here, but with a different direction. Our normal vector is the one that I show you, and it points up from the surface. Here's the field above, which we've already written down. Here's the field below, just changing this sign. So now take the difference. So we take the difference in these vectors here. So we just write it all in. And what do we get? Well, you can see we get a half here and a half here with a plus sign. So when we add those together, we get the change in these two vectors, namely sigma over epsilon naught times n hat. And that was the boundary condition that we developed. So we say that's okay, and it's consistent with our equation earlier. What have we done? We've just simply shown that if we go from this side to this side, the change in the E field, so here's E down, that's E below, here's E above, and the change that occurs is equal to this quantity here. Well, let's look at a charged parallel plate capacitor. Let's say that we have sigma plus sigma here, minus sigma here. We know the E field, it's equal to this quantity here. So the question is, if we go across these interfaces here, so let's take this interface, we have the n hat vector here that points from left to right, so for this surface right here. Let's look at the E field. It goes above the surface. It's equal to this quantity here, as we have just stated up here. It's uniform in that space. We're inside a metal, so therefore below is 0. So now take the difference. This is 0. So we end up with this quantity right here, which is again back to our boundary condition that we derive for E total. That's okay. So we can do the same thing over here. We just change the direction of n hat, and we still have 0 in this part of the system. So here's E above, and it goes in the minus direction, and it has a minus sign because of the charge. The charge is negative. When we take the difference, so we take E above minus E below, we end up with the same thing. So we have sigma over epsilon naught n hat. You can see then that very special cases are easy to work out, and you can see that the boundary conditions work. So that's okay too. Well, let's take a look at a little bit different geometry. Suppose we have a hollow cylindrical tube. It can carry a surface charge density sigma, and it's going to be uniform. Now just to remind you, this is not a conductor. This is a sheet of charge. This corresponds to a linear charge density, which we can define as lambda, equal to the charge density times 2 pi r, which gives you the charge per unit length on this cylinder. And r, of course, is the radius. We're going to use Gauss's law. There's no enclosed charge inside, so inside we have E equals 0. The Gauss's surface to prove that would be a cylinder inside like this, where this radius here is less than capital R. So as long as this radius is less than R, we're going to get 0. What about outside? We've done this before, so you take this cylinder outside and you analyze it, and the E field you get is 2 lambda over 4 pi epsilon naught s. So in other words, this looks like a line charge with charge density lambda. Here we have S greater than R, N is the perpendicular distance to the field point, and E points radially outward for positive charge. And so if I make this a vector, I should put in an S hat, and that will be fine. We have two values of E. Inside is 0. Outside is this quantity here. And we've already said that E points radial. Let's look at E above. That's what I just said. This could have been S hat. We'll call it N hat. E below. So take the difference. And so we use these equations for the difference. All we have is E above, like here. So the change in the E field to go to 0 value will be equal to this. Now put in our value of lambda, which we wrote down earlier, sigma times 2 pi r, and cancel everything, and we end up with sigma over epsilon n hat. For this geometry here, for a shell of charge, not a conductor, we end up satisfying our boundary condition as we saw before. So that's okay. Let's look at another case. This is a shell of charge that's on a sphere. So we have sigma, the constant, and I wanted to review the potential. We're going to be looking at the potential and the gradient. So here's the potential that we derived, and we derived that by brute force. This is the fundamental definition of the potential in terms of charge density, and this is the field point, this is the source point. If you remember, we did this for both inside and outside. For outside, we ended up with this quantity here. Remember that we could have replaced Z with little r, so this could be a little r here. Inside was constant. We had sigma capital R over epsilon 0. So this doesn't change with position. So if we plot this, we have this plot here. This is the constant value equal to this quantity here, and as soon as we hit R, then we have this behavior here. Remember, this could be little r, and this would be the way it falls, namely 1 over R or 1 over Z. So this is the potential, and what we're interested in is what happens right here at the boundary. Taking our equations, so I'll just repeat, here are the two equations. So here we have outside, here we have inside, and I've changed Z to little r. If we take inside to be below and outside to be above, then the plus r direction is the direction of n hat. We set little r equal to r, which is the boundary, and we do that for both expressions. We only actually have to do it for outside. So outside, setting r equal to capital R, we get this quantity right here. But if you look at what it is inside, this was what we derived. This is the V inside, the constant value. What you see is that at the position capital R, R equal capital R, we indeed have the two quantities equal, and that's that R equals capital R. That's the case here. You can see that they're equal at this point right here. So that's okay. Let's look at the gradient inside and outside of this spherical shell. And just remember that r hat is equal to n hat, and r is n, where this is the variable perpendicular to the surface. We're calling outside above and inside below. Take the expression we had for the potential above, and so we're taking the gradient of this quantity here, which is what we had for that potential. This is in spherical coordinates, so what that turns out is simply the partial with respect to r. So take that, and we end up with this quantity here, which is equal to this quantity right here. The gradient above is equal to this. The gradient below, remember that V inside was a constant, so we get 0. So take the difference of the gradients, and we end up, of course, with just the gradient above, but that we evaluate at the interface, which is r equals capital R. And when we do that, we get the change in the gradient, including the sign. We get the correct value for the change in the gradient. That's okay. What we've done is, again, taking another special case and ask, does this boundary condition hold? And the answer is yes. So all of these are just simply trying to get you to the point where you have some confidence that these boundary conditions are actually correct. Let's make some remarks here. The boundary conditions are necessary to obtain solutions for V and E in the space surrounding surfaces or between surfaces that are charged. And this can be surfaces with conductors or without. And the other comment is we often deal with surfaces that are at fixed potentials, so the boundary conditions involve V and sometimes the gradient of V. So these are relevant.